This is Dr.S.Prasanna, Assistant Professor of Mathematics, Pingal Government College for Women, Varangal. In the previous video lesson, I have given two problems as an exercise for the students, and I hope you have come up with your own solutions. And now I want to fetch the solutions for those who couldn't get any solution for these problems, and let us see how we can do this, how can we solve these problems. So the problem given to us is, consider the set vector space R3 with usual addition and scalar multiplication, and R3 in notational form is given as set consisting of elements of the form x1, x2, x3 column vectors such that x1, x2, x3, the entries are real numbers. And we are required to show that capital H is equal to set of the column vectors x1, x2, 0 such that x1, x2 are real numbers is a subspace of R3. So we are given the vector space R3 and a subset H of it, and we are required to prove that H is a subspace of R3. And if you recall the definition of subspace, a non-empty subset H of a vector space V will be a subspace of it if three conditions are satisfied. And the first condition is the zero vector should lie in that set H. The second condition is the vector addition should be satisfied in H. And the final and third condition is the scalar multiplication should exist in H. If these three properties or these three conditions are in H, then only H can be a subspace of given vector space V. So in the same manner, here that given set H can be a subspace of the given vector space R3 if the set conditions, if the three set conditions are satisfied in H. Let us see whether they are satisfied, and if so, how? Let us see. The vector space given is R3, and R3 is given as set consisting of the column vectors x1, x2, x3 such that the entries x1, x2, x3 are real numbers. Now consider the set H. H is equal to set of x1, x2, 0 such that x1, x2 belongs to R. That means x1, x2 are real numbers. And now we can see that as the third entry of H is fixed as 0 and the other two entries are variables, we can see that somehow H is a column vector consisting of all the three entries as real numbers, and hence H can be a subset of R3. And if x1, x2 are also zeros, then the zero vector will be in H. Let us see whether that happens in H and how. The first condition, to verify the first condition, the zero vector of R3, as we know, it is 0 bar, which is given by the column vector 0, 0, 0 for 0 belongs to R, the real number 0. So also we can say that 0 bar is equal to 0, 0, 0 belongs to H, as for the reason that the third entry in this column vector is 0 and the first two entries can be any real number. So we are taking the first two entries as also the real number 0 itself. Hence we can see that the element 0, 0, 0, which is 0 bar, is in H. So that is how the vector 0 bar belongs to H, and hence the first condition is satisfied in the set H. Now to verify the vector addition property or vector addition condition in H, we need two vectors from H, and I am taking u bar comma v bar as elements of H, and as they are in H, they should be of the form x1 x2 0 by the equation 1, by the column vector x1 x2 0 by the equation 1. And here I am taking u bar as x1 x2 0 and v bar as y1 y2 0, and here we can see in both the vectors u bar and v bar, the third entry, the third element or third row element is 0, and the first two entries from both the vectors are real numbers, that is x1 x2 y1 y2 all are real numbers. Now consider what is u bar plus v bar. Let us see what is it equal to. U bar plus v bar is equal to x1 x2 0 plus y1 y2 0, and that gives you x1 plus y1 x2 plus y2, and 0 plus 0 is 0. And we here also we can see in the resultant column vector, the first two entries are real numbers and the third entry is fixed number 0. And the first two entries we can say they are real numbers for the reason that x1 each is the sum of two real numbers, and we know that sum of two real numbers is again a real number, and that is the reason u bar plus v bar belongs to H. Since by equation 1 x1 plus y1 comma x2 plus y2 belongs to R, that is the reason I have mentioned here. And now we can say that u bar plus v bar is an element of H, and hence the vector addition is satisfied in H. And the third and last condition for H to be a subspace is scalar multiplication. And now let us verify whether the scalar multiplication is satisfied in H. For that we need a scalar, and I have taken C as a scalar, and it can be any scalar, as C we are not giving it as a specific number, it can take any real value, so C is any scalar. And Cu bar is equal to C times x1 x2 0, and that is equal to Cx1 Cx2 0 by scalar multiplication of column vectors in R3, and here we can write Cx1 Cx2 0 as the resultant column vector by the definition of scalar multiplication Cu bar. And now we can see that the last entry in the resultant column vector, that is Cx1 Cx2 0 are the entries. Here we can see the third entry is 0, fixed number, and we also know that the first two entries Cx1 and Cx2 are the scalar multiples of two real numbers x1 x2, where C itself is also a real number, and hence those two are also real numbers. And now we can see that this is just like the element of the form in the set H. So this is an element of H, we can say. And since by 1 I have written as since by 1 and Cx1 comma Cx2 belongs to R, by these two reasons we can say that Cx1 Cx2 0 the column vector belongs to H. Therefore finally we could say that Cu bar, the scalar multiple of u bar by a scalar C, is in H. Therefore H is a subspace of R3, as all the three conditions are satisfied in H, and H is a subset of R3, which is a vector space. We can say that H is a subspace of R3. Here I am making a note point, and in that I have mentioned what is the geometrical purview of this set H. And when viewed geometrically, the above subspace H is XOY plane, as it is the Z coefficient, the Z entry is always 0, that is the third entry is always 0. That shows that all the elements of H are in XOY plane, and that is how H represents a subspace in XOY plane. And we can also see that this passes through the origin, because even x1 and x2 can take the value 0 0 and can be 0 0 0 can be an element of H by taking this form with the third entry as 0. So we can say that every element of H, not every element of H, the set H, the subspace H passes through the origin. One of the elements of H is origin, that is 0 0 0, the 0 vector. And note that, make a note that any subspace of R3 which is a plane must pass through the origin. If we consider any subset of R3, if it doesn't pass through the origin, then we can say that the 0 vector will not be in that subset, and hence it cannot be a subspace of R3. So if some subset of R3 is to be subspace of R3, then it should possess 0 vector, and that is how it should pass through the origin. So every plane that passes through the origin will be a subspace of R3 is the final conclusion. Here I have given you a plane passing through passing through the origin. It may be XOY plane or YOZ plane or ZOX plane. Now moving on to the third problem. Let capital F be a fixed 3x2 matrix, and let capital H be the set of all matrices A in capital M 2x4 with the property that FA is equal to O, where O is the 0 matrix. Verify if capital H is a subspace of M 2x4, and this is the problem given to us. And here capital F is a fixed 3x2 order matrix, and H is the set of all matrices matrices A H is a subset of M24. That means M2x4 is the vector space consisting of all 2x4 ordered matrices, and H is a subset of it. And F, which is a 3x2 matrix, when multiplied to the element of H from left side, that means FA, gives you the 0 matrix. FA will be equal to O, and where O is the 0 matrix. So if this happens, then that A will be the element of the subset H of M2x4. So a matrix A to be an element of the subset H of M2x4 is that the A should satisfy the condition FA is equal to O, where F is a fixed matrix of order 3x2. So how we can do this? Let us see. M2x4 is set of all matrices of the form 2x4 matrices which can be taken wherein the entries can be taken like this: x1, x2, x3, x4 as first row, x5, x6, x7, x8 as the second row. Here we can see that each xi is a real number where I varies from 1 to 8. I is taking values from 1 to 8 integer values. O is the 0 matrix in M2x4, and O is the 0 matrix in the vector space M2x4. Now by the condition, mentioning the condition FA is equal to O, we can define the set H in a notational form like this: H is equal to set of A belongs to M2x4, all those matrices of M2x4 which satisfy the condition FA is equal to O will lie in the set H. So for that reason H is defined as H is equal to set of A belongs to M2 by 4 such that FA is equal to O, where F is a fixed 3 by 2 matrix as given in the problem itself. Now H will consist of, as A belongs to M2 by 4, A will be a matrix of order 2 by 4. So H consists of, the set H consists of all 2 by 4 matrices. So H is equal to A 2 by 4 such that FA is equal to O 3 by 4. Do remember that F is a matrix of order 3 by 2 and A is a matrix of order 2 by 4. When we multiply a 3 by 2 matrix with a 2 by 4 matrix, we are going to get a 3 by 4 matrix, and that too here it is O, that is 0 matrix. So when F is multiplied to A, we will get a 0 matrix of order 3 by 4. And so F, now I want to show that capital H, the set capital H consists of the 0, that 0 vector which is O. I should have given O dash here. So okay, that O is different from this O, that FA is equal to O, here O is of order 3 by 4. Now which I am mentioning about is some other 0 vector, and that is a 0 matrix of order 2 by 4. And here I am claiming that this O in bit 1, in part 1, is a 0 vector of M2 by 4. In the vector space M2 by 4, 0 vector I am taking as O, which is of order 2 by 4. That means it should have 2 rows and 4 columns. And this O, which is an element of M2 by 4, which is a general vector of M2 by 4, which can be treated as a vector of M2 by 4, satisfies the condition FA is equal to O, where in place of A, now I am taking O2 by 4 and seeing that F3 by 2 into this O2 by 4 is again giving rise to the 0 matrix which is defined, which is of order 3 by 4, which is denoted by O3 by 4. So in place of A, I can take O2 by 4 matrix. So O2 by 4 is a 0 matrix of order 2 by 4 and that belongs to the set H. Therefore 0 vector is in the set H. The first condition of subspace is satisfied in H. Now move on to the second condition. See whether the second condition of subspace is satisfied in the set H, we need two matrices, and those two matrices I have taken as A comma B, and which are in the set H. Now as A comma B belongs to the set H, we can say that as A belongs to H, FA should be O, and as B belongs to H, FB should be O, as by the definition of the set H. As they are elements of H, they should satisfy the condition FA is equal to O, and for B also the condition should be satisfied, and that is how we got FB is equal to O. Now consider F times A plus B, and this is equal to FA plus FB, and FA plus FB by property of matrices we could write like this. This is a distributive property which is satisfied in the in all matrices which can be added and which can be multiplied, which can be commuted. So F times A plus B is equal to FA plus FB for such matrices, and this is equal to O plus O by the reason that A comma B belongs to H. As we have written in the above line, in the above step, Fa is O and Fb is also O, and O plus O of same order give you the O itself, which is a 0 matrix. And here we can see that F times A plus B is equal to O, and that means A plus B is satisfying the condition Fa is equal to O, and hence A plus B belongs to H. Now A plus B belongs to H means the vector addition is satisfied in the set H, subset H of M2 by 4. Now to verify the third condition, consider a scalar C. So I have taken C as a scalar, any scalar, then F times Ca is equal to C times Fa, and Fa we already know that it is O, and so C times O is equal to O. By the matrix scalar multiplication of matrix, when we multiply C to every element which is 0 of the matrix O, we are going to get the 0 matrix only, and which is O. So F times Ca is equal to O, and this means Ca. F times a matrix is equal to O means that particular matrix will be an element of H. So Ca belongs to H. Therefore, all the three conditions of subspace are satisfied in H, and H is a subspace of M2 by 4. Now let us see the statement of a theorem, and let us prove that theorem also. This theorem states that the intersection H intersection K of two subspaces H and K of V is a subspace of V, and that means intersection of two subspaces of a vector space is again a subspace of that vector space. Or if H and K are two subspaces of a vector space V, then H intersection K is also a subspace of V. And there is further written that given in the statement that, but the union H union K need not necessarily be a subspace of V. But we can say that the intersection is always a subspace of the given vector space, but it need not be necessary that their union may be a subspace of V. So in some particular cases, H union K may be a subspace of V, but in general it is not true. So that is what we have to prove now. So let us move on to the proof now. Given V is a vector space, it is further given that H and K are subspaces of two subspaces of V. Now H intersection K is to be shown as subspace of the vector space V. So let us see what is the set H intersection K. H intersection K consists of all the vectors U bar such that U bar is an element of H, and at the same time U bar is an element of K. That means H intersection K is equal to set of U bar such that U bar belongs to H and U bar belongs to K. Now let us move on to verify the conditions of subspace for this set H intersection K. And here we can see that the 0 vector 0 bar is in the vector space V, because as it is already a vector space and it should consist of the 0 vector 0 bar. By the third axiom out of the 10 axioms of the definition of vector space, the third axiom gives the existence of additive identity, which is the 0 vector. So by the definition of vector space V, we have the 0 vector belongs to the set V. Now if 0 vector is 0 vector of the vector space V, we can say that that is a 0 vector of the two subspaces H and K of V. So 0 bar belongs to H and 0 bar belongs to K. And 0 bar belongs to H is by the reason that H is a subspace of V, and 0 bar belongs to K is true by the reason that K is a subspace of V. So now we could see that 0 bar belongs to H and at the same time 0 bar belongs to K. This means 0 bar belongs to their intersection also. So 0 bar belongs to H intersection K. That means 0 vector is in H intersection K, in the set H intersection K. So the first condition, which is the existence of 0 vector in the set H intersection K, is satisfied. So next, moving on to the addition of vector addition, is whether it is satisfied in H intersection K or not. To see that, to verify that, we need two vectors u bar comma v bar are the two vectors I have taken in H intersection K, and if u bar comma v bar belongs to H intersection K, then we can say that those two elements are elements of H and at the same time those two are elements of K also. So u bar comma v bar, by the definition of H intersection K, if some element belongs to H intersection K, then that element should be an element of H and at the same time it should be an element of K. So u bar comma v bar belongs to H and u bar comma v bar belongs to K whenever u bar comma v bar belongs to H intersection K. Now, as H is a subspace of V, we can say that u bar plus v bar belongs to H when u bar comma v bar belongs to H. And similarly, we can also say that u bar plus v bar belongs to K as u bar comma v bar belongs to K. This happens by the reason that H and K are subspaces of V. So we have seen that in the above step, u bar plus v bar belongs to H and u bar plus v bar belongs to K. This shows that u bar plus v bar belongs to their intersection also. So u bar plus v bar belongs to H intersection K. Now we have proved the second condition of subspace also in the set H intersection K. Now moving on to the third condition, which is scalar multiplication. To be verified in the set H intersection K, we need a scalar C and a vector u bar, and hence take a C, let C be any scalar and u bar belongs to H intersection K. Now, as earlier in the condition in condition 2 what we have seen, if some element belongs to H intersection K, then that should belong to both the sets H and K. So here u bar belongs to H intersection K implies u bar belongs to H and u bar belongs to K. Then if u bar belongs to H and C is any scalar, by the property of subspace of H, which is a subspace, we can say that the scalar multiplication exists in H, and that is how Cu bar belongs to H. And similarly, we can say that Cu bar belongs to K, as K is a subspace of V, that is already given to us. So Cu bar belongs to H and Cu bar belongs to K by the reason that H and K are subspaces of V. And if this element Cu bar belongs to both the sets H and K, then we can say that belongs to their intersection also. Therefore, that is how Cu bar belongs to H intersection K. Now, by this condition, by all the three conditions, as all the three conditions are satisfied, we can say that H intersection K is also a subspace of V. But in the theorem, it is further stated that H union K need not be a subspace of V. For that, to prove that, I am taking two specific examples, two specific sets, and then I am also going to take two specific vectors from that set, and want to show that H union K need not be a subspace of R2. So for that, I am taking a specific set H as X set consisting of ordered pairs x comma minus x, such that X belongs to R. So H is a subset of the vector space R2. And I am taking another set K which consists of the elements x comma 2x such that X belongs to R. Here we can see that H and K both are subsets of the vector space R2. Now consider their union. H union K is equal to set of all the elements, either they may be of the form x comma minus x or they may be of the form x comma 2x. So that is how H union K consists of the elements x comma minus x and at the same time x comma 2x form elements wherein x is a real number such that x belongs to R. Now consider two vectors. Now we want to prove that H union K is not a subspace of R2. So to disprove that H union K is a subspace, we need two vectors from H union K, and I am taking those two vectors as one u bar and the other one I named it as v bar, and u bar I am taking with the specific entries 2 comma minus 2 and v bar I am taking 4 comma 8. We can see that u bar is of the form x comma minus x and v bar is of the form x comma 2x. So I have taken, here we have seen that H union K consists of both types of elements, both types of ordered pairs x comma minus x and x comma 2x, and for that reason when I need to take two vectors, when I need to choose two vectors from H union K, I have taken one in the form x comma minus x and other in the form x comma 2x. And here u bar is equal to 2 comma minus 2 is of the form x comma minus x and v bar 4 comma 8 is of the form x comma 2x. Now let us see what is u bar plus v bar. U bar plus v bar is equal to 2 comma minus 2 plus 4 comma 8, and that gives you, by adding corresponding elements and writing in the corresponding position, we get it the resultant vector as 6 comma 6. But we can see 6 comma 6 is neither of the form, it is neither of the form x comma minus x nor of the form x comma 2x. Then it cannot be an element of H union K, and hence u bar plus v bar does not belong to the set H union K. And if that is so, if u bar plus v bar does not belong to H union K, then the second condition of the definition of subspace is not satisfied in the set H union K, and hence H union K cannot be a subspace of the vector space R2. So H union K is not a subspace of R2. So hence we can in general say that H union K need not necessarily be a subspace even if H and K are subspaces of a given vector space. So this is the theorem we have proved. So the theorem statement is the intersection H intersection K of two subspaces is a subspace, but the union need not be a subspace of V. So to prove H intersection K as subspace, we have proved all the three verified all the three conditions of subspace of a vector space. But to prove H union K is not a subspace, we have given the specific we have considered a specific example for H and K and could prove that. Now the last topic of subspaces is sum of two subspaces. The sum of two subspaces is also a set which can be defined like this. Let us go through the definition. The sum of two subspaces H and K is denoted by H plus K. It is a set and it is defined as H plus K is equal to set of W bar. H plus K also consists of vectors W bar, where W bar is of the form U bar plus V bar. where W bar is the sum of two vectors U bar and V bar, and for some U bar belongs to H and V bar belongs to K. That means W bar is the sum of vectors from sum of two vectors from H and K, so that the first one vector is from H and the second vector or other vector is from K. There is a theorem on sum of two subspaces. Let us see what that theorem is. What is the statement of that theorem? If H and K are two subspaces of a vector space V, then H plus K is also a subspace of V. And what is the theorem statement? We can say that even as H intersection K is a subspace whenever H and K are two subspaces of a given vector space V, here also we can say that the sum of two subspaces H and K, which is denoted by H plus K, is also a subspace of V. So how can we prove that H plus K is a subspace of V? Let us see. And as the earlier that we have seen in the problems, or either in the problems or in the theorem proof, we have seen that to prove a given set as a subspace of given vector space, we need to show that set satisfies all the three conditions of definition of subspace. And those three conditions are existence of zero vector, existence of vector addition, and existence of scalar multiplication in that particular set. So here H plus K is the set to be proved as subspace. So we are given that H and K are two subspaces of a vector space V, and we have H plus K is equal to set of W bar such that W bar is equal to H bar plus K bar. For some H bar belongs to H and K bar belongs to K. Now H plus K is a subset of V. H plus K is a subset of V. We can have it obviously for the reason that whatever be the element of H plus K, that is a vector, and the sum of two vectors from H and K is again a vector from the set V itself, as V is a vector space by the first axiom itself, the closure axiom. We know that H bar plus K bar should belong to V again. So that is how H plus K is a subset of V. And let us see whether the zero vector exists in H plus K. We know that H and K are subspaces of V, and for that reason 0 bar belongs to H, and at the same time 0 bar belongs to K. If 0 bar belongs to H and 0 bar belongs to K, and then 0 bar plus 0 bar, which is a sum of a vector from H and other vector from K. If we suppose this first 0 bar is from H and the second 0 bar is from K, then their sum should belong to the set H plus K. But what is 0 bar plus 0 bar? That is again the 0 vector 0 bar itself. And that is how the 0 vector of V is in the set H plus K. Now moving on to the second condition, take the two vectors U bar comma V bar belongs to H plus K. Now U bar is equal to H1 plus K1 and V bar is equal to H2 plus K2 for some H1 comma H2 belongs to H and K1 comma K2 belongs to K. In the two vectors U bar and V bar, the first two elements should be taken from the set H, and K1 comma K2, the second two elements should be taken from the other set K. Now U bar plus V bar is equal to H1 plus K1 plus H2 plus K2, and this can be rewritten as or rearranged as H1 plus H2 plus K1 plus K2 by the associativity in the subspaces. They may be H or as when we consider H and K together, we can say that this is the associativity from the vector space V itself. So H1 plus H2 plus K1 plus K2 taken in separate brackets, we can see that each bracket belongs to the sets H and K respectively, and that is how that element belongs to H plus K. And here I have mentioned the reason, since H1 bar plus H2 bar belongs to H and K1 bar plus K2 bar belongs to K are subspaces, and H and K are subspaces. These two belongs to H and K. Now H plus K is closed under addition. We could prove that H plus K, the sum of two subspaces H and K, which is H plus K, is closed under addition. That means satisfies the vector addition property. And third one, let C be any scalar, then Cu bar is equal to C times H1 plus K1, and this is equal to CH1 plus CK1, and this belongs to H plus K since H and K are subspaces. And on the whole, we can say that H plus K is closed under scalar multiplication, and by the conditions 1, 2 and 3 we can conclude that H plus K is a subspace of V. So the sum of two subspaces which can be defined like this: H plus K is equal to set of the vectors W bar, set of all vectors W of the form W bar, where W bar is U bar plus V bar, taking U bar from H and V bar from K. That constitutes the set H plus K, which is called sum of two subspaces H and K. And now we have proved that H plus K, the sum of two subspaces, is also a subspace whenever the two the two sets we have considered are subspaces by themselves. So when H and K are subspaces, H plus K is also a subspace. That is the conclusion. So with this we have finished off the topic subspaces, and in the next video lesson we can move on to the next topic, and which is the most important, or we can say which plays a vital role in the further study of linear algebra, and that term or that concept is linear combination. And after that we can move on to the another important concept, span. So tomorrow in the next video lesson we can go through the important concept linear combination. So with this I will sign off.